Hi, this is Mrs. D. We're going to be learning about exponential modeling, the calculus side of things eventually, but we're going to start with some pre-calculus know-how that hopefully you have in your arsenal of knowledge. So first things first, I have this terrible hand drawing of a growth function, and I'm asking you to observe anything you might notice. I mean, maybe at first you noticed it was in a growth function. I'm observing an asymptote, and I'm also observing that this is very much not to scale. Those values don't at all seem to be lining up with this axis. If that's 3,000 and that's 12,000, wowzer, quite a jump. But let's start quantifying that jump. So I've got time 2, time 4, those are possibly years, let's say. So as we try to quantify this, we're going to try to express an equation for this growth. And it would be important to know the rate of growth, which is pretty steep here on this one. What is the rate of growth? And maybe you observe some quadrupling, perhaps some doubling, whichever way you see it. I'm going to go with the doubling idea first. So year 2, year 4, there's definitely a year 3 in between there. By my number sense, your number sense, everyone's number sense, maybe we could deduce that the value there in the third year would be 6,000, and then that would fit the pattern of doubling. So let's say we view it as doubling every year. And if that's the case, that is a growth rate of 100%. Here's how the function would look. Money, 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 if that's what this model is for, would be, let's see, 1,500 times 2 to the t, where t is the number of years and the initial value is 1,500. I didn't show that. That's probably what this number would be, right? 1,500. Wonderful. Let's say you observed quadrupling. This could be an equivalent form of this model. The initial value would be the same, so maybe we say money equals 1,500, but if we wanted to express the quadrupling, a base of 4 would be necessary. And notice that that occurred, a quadrupling, not every year, but every 2 years, and so we would represent that with a t over 2 exponent. Number-wise, this should make sense because 4 to the 1/2 power is the equivalent of 2, and we are just raising that 2 to the t, so this is the same exact expression, just using a different base. How about this one? This one's much less obvious, but hopefully you see some decay. And for a decay model, the base would have to be less than 1. Maybe you can start to notice what the base might be, or how the change is occurring year to year there. The base is less than 1. Do you notice that we are losing 20%? Are those percents that you know? We have 400, 20% of that would be 80. So here's a loss of 80. Then this loss is different because it's the same percent but of a different amount. And so the loss goes on and on. Here we have lost 64. Again, you're losing less and less, which kind of is the reason the graph will look like that. A decay model, kind of leveling off. Two things we don't know. One, what exactly is that loss? Maybe you do know it's 20%. Here's a way to figure that out if you didn't know that. Take each subsequent value and divide it. And what you'll notice is that these come out to decimals. Yes, they do. But they tell you kind of what's remaining. So here, for example, the 256 is 80% of the 320 that was there prior. Likewise, the 320 is 80% of the 400 that was there prior. So this loss of 20%, as we write this model, the money, or the value, maybe we use V instead of Y, whatever strikes your fancy. I would have to know the initial amount. Then I'm going to multiply by 0.8. That's my decision. 0.8 to the t, because that base is less than 1. We've lost, but we haven't lost all of it. The amount of loss is 20%, and 100% minus 20% leaves us with that 80%, and that is also calculated here. To find that initial value, I would start working backwards using my calculator and divide by 0.8, divide by 0.8. and you can find that initial value, which is not a whole number, but we have $781.25. Maybe you broke the piggy bank, combined your birthday money, and that's what you're able to start this account with. And there is our model. The initial value, the base, which represents our constant multiplier, term to term here, year to year, and then the exponent. It is an exponential decay function. There you have it. Now we're going to dig into the calculus. So, for calculus to make sense, we are talking about numbers. I'll use our first example because that was maybe more obvious. These subsequent numbers are related, or the rate is related to the values. So this is our doubling example. And so the rate of growth, how much it grows by, depends very much on what the current amount is. So this is called the law of exponential change. It's very intuitive, kind of common sense, I hope. If y changes at a rate that's proportional to the amount present, so this 1500, that change is the change that brings us to the next amount, or we could say the next amount is a multiplier of the previous amount, a multiplier of the previous amount. Then we can express with a derivative, very arbitrarily here, dy dt equals ky, and in our last video we were separating variables, so we'll do that here and get the conclusion of the exponential law of change. If I separate, I'm going to divide by y and multiply by dt. Now I will integrate, and this gives us a very, very, very generic form for any differential equation that looks like this. Our conclusion will be that the model, natural log of y, equals kt plus c, should be fitting to that function, no matter what it is. E will be used to undo the logarithm, and we write y equals, remember this exponent of c is just another power of e, so e to the kt times e to the c, and you'll never see it written that way. It will almost always be expressed where this is a number, remember. So that number, that c, is multiplied by e to the kt. It's always going to be an exponential model. That shouldn't surprise us. That c is oftentimes an initial value. As we wrote our models, that was the initial value that was the multiplier in front. This would hold true as long as the horizontal asymptote is at 0. The constant that you see in the differential equation is also the constant you see in the exponent, as you will also notice in our next example. Here we have a radioactive isotope. Radioactive. That means it's kind of decaying quickly. It's shriveling and it's losing mass. You probably can't see it happening, but it's all chemical reactions. So according to this differential equation, this is how the isotope is decaying. And notice first of all that we have a negative. If a derivative is negative, then it's a negative growth, which I wouldn't even call growth. It's just negative change. I'm anticipating that this will probably be an exponential decay function. If there's negative change, it's less and less over time. So I'll separate the variables as we just did with this particular example, though. Dividing by y, multiplying by dt. And it shouldn't surprise us as we go through the integration process or finding the antiderivative that this model is exponential. So I have negative 0.145, that's just a constant rate of change or some linear function. Remember the plus c. Solving for y, we'll have y equals c e to the negative 0.145t. Now that'd be hunky-dory if that's all we were looking for, but they're asking us to determine the half-life of the substance. Do you know what half-life is? Let me tell you what I know. Half-life is a measure of time. It's how long, in years, maybe, months, could be seconds. It's the time that it takes to lose half of the mass. So we don't even know the initial amount of mass here that this substance had, or the size of the sample, let's say, but this number would probably be that starting amount. And if we're trying to determine the half-life, We want to get to half of that. So if we lose half of C, we're left with half of C. So I'm going to solve this without having any other given information. It can be done. Watch. When do we get to half the amount? So y is like the mass. The mass is unknown, but arbitrarily it's half of what it was. So if I try to solve for t here, let's see how this works out. So we have c multiplied by the exponential function here with a negative power. That's showing decay. A person might want to multiply both sides by 2. I think that's what we did in class. That gets rid of the fraction confusion, perhaps. Now the constant, the c is still there. Well, now it's not. I'm going to divide both sides by c. So I have 1 equals 2e to the negative 0.145t. And in this scenario, if I divide by 2, all I have left to do is kind of undo e. So that will require a logarithm. A lot of times we're using exponentials to undo logarithms. Here we're using a logarithm to undo the exponential. So whatever natural log of 1/2 is, and then that number is not my time just yet. You'll probably notice it's a negative number. Time shouldn't be negative. Store that number in your calculator, just leave it there, and the last step to solve for t will be to divide. Divide by negative 0.145 and see that you get an answer of 4.780 years. 4.780 years. That's assuming time is measured in years. It very well could be 4.780 minutes or something like that, depending on how radioactive it is. But there we have solved for the half-life. They could ask you to solve for how much mass is left after 15 years, and you would just have to determine your model specifically. Some other conditions would need to be given, but work with the exponential models to find the answers to the questions that you have. Happy solving. Calculus rocks. See you next time. Mrs. D signing out.